Welcome to the Math 1, Unit 7, Lesson 7, Summary Video, Circle C, Racing Pigs. This lesson is a Solidify Understanding task, which takes concepts developed previously and helps you formalize those ideas. The purpose of this lesson is to solidify understanding of how to build a quadratic function that models area with a fixed perimeter, make sense of the key features, and make connections between the various representations, and examine the relationship between the x-intercepts and the vertex. Dennis Cook runs the Circle C Racing Pigs on the Hogway Speedway at the North Carolina State Fair. Everyone loves to watch the swift swine rush around the track to get a cheese puff, which is what they're awarded at the end of the race. Mr. Cook wants to create a pen outside of the pig trailer so that the pigs can meet and greet their fans. He will use one side of the trailer for part of the pen and has enough money for 80 feet of fencing material. So you can see in the diagram on the screen, we have the pig trailer, which is the large rectangle, and the pig trailer is going to make up one of the four sides of the meet and greet pen. So the 80 feet of fencing that he's going to use for the perimeter of the meet and greet pen is going to be made up of only those three yellow sides that you see. So that's important to keep in mind. So first, we want to make sure that we define our variables. So we know that we have only three sides of our pen, and we know that these two opposite sides are going to be the same value. And we're going to let those sides be represented with x, and that's going to be the width of our pen. So the width of our pen is x, and so then the length would be the 80 total feet of fencing. Altogether, this is 80 total feet. So the 80 total feet of fencing minus the two widths. So this is what our length is going to be. And so it says, what are some possible dimensions for the pen? Use multiple representations to show your possibilities. So you could use graph paper and you could create some area models with this. We could create a table. From the table, we can create a graph. And so in this video, we're going to look at what this would look like with a table. And so you can see here, we have our dimensions of the width, and then the dimensions of the length. And in the second question, it starts talking about the area of the pen. And so what we want to do is we want to get the most space for the pigs as possible, which means we want to have the greatest area. And so we're going to look at the relationship between the width and the length of the three-sided pen, knowing that we can only use 80 feet of fencing, and how that affects the area. So what we're really comparing is how when we adjust the x value or the width, when we increase or decrease that width, what's happening to the area of our pen. And so as you notice, I did not include all of the values, all of the possible values for the width, because of course we could have a width of 3 and 4 and 6, 7, 8. So we could have all of these different widths. I started out with 0 because if we had a width of 0, we really wouldn't have a pen. We would just have a straight line of our length, which would be 80 feet. And so you can see here that's represented in the table. If we had no width, we would only have length, therefore we would have no area. We would not have an enclosure. If the width were 1, then this side would be 1, this side would be 1, so that would be 2. So we're doubling the side of, or the length of one width, and we're subtracting that from the total of 80 feet. So if my width is 1, then my length would be 78, and my area would be 78, and so on. And so we go all the way down the table until we get down to a width of 40. And so then if we had 40 on this side and 40 on this side, that would use up our total 80 feet worth of fencing, and we would have nothing left for the length. So we would have a width of 40, a length of 0, and an area of 0, which again would leave us with no enclosure. If you notice, as we're increasing our width, first of all, you can see as we get up here to 20, a width of 20, that would be 20 here, 20 here, and 40 here. And so that would use up all of our 80 feet of fencing, which would give us the largest possible area of 800 feet. So you can see that as we're increasing our width, our area is increasing. Well, you could also say, well, our width is increasing here, it's continuing to increase, but now our area is decreasing. But if we think about it in terms of a rectangle versus a square, if we look back here and we say, okay, well, if the width is 1 foot and the length is 78, then we've got a rectangle with the dimensions of 1 by 78. So that would be a really short width and a really long length. So that would be a long, skinny rectangle. And notice that that has a small area. As our width increases and its value becomes closer to our length, our area is also going to increase. And so that would be the same as if we had a rectangle with a perimeter of 8. We could have side lengths of 3 by 1, which would give us an area of 3, or we could have a rectangle with side lengths of 2 by 2, that would give us a perimeter of 8 also, but it would then give us an area of 4. And so as the length and the width values become closer together, then we have a rectangle with a larger area. And so that's what we're seeing here. And then as we move down the table, even though it's a little distorted in here due to the fact that we are only looking at a 3-sided figure instead of a 4, but as we get further down the table, we can see then as our width and our length become further apart from each other, our area again starts to decrease. So in the previous couple lessons, we've been looking at the features of quadratic functions, and one of the things that we've been talking about is that common second difference. And so we can see the first difference here between these two values is 78 and 74. That second difference is a -4. And so if we were to fill in all of the values of x and go all the way down our table, we would see that between each of these outputs or y values, we would have a common second difference of -4. We also talked in the previous lesson about how when we look at the maximum value, this is our maximum value, this 800 square feet of area, how it's symmetrical in the table on both sides, on either side of that maximum value. So going from 800, we have 750 on either side, and then we have 600, we have 350, and notice that my value is 20, and even though I'm not showing every single possible x value, I'm skipping by 5 here and 5 here, and so we can see that it's still symmetrical. Notice that our differences, our first differences, are also symmetrical. They're just opposite values. And so when we look at this in terms of a graph, these are our independent variables, or our x variables. That's represented on our x-axis. This is the width in relation to our area. So the area is a function of the width, and the area is represented on our y-axis. We can see some of the features of our quadratic function clearly here in both the table and the graph. We can see our x-intercepts in the table at 0, 0 and 40, 0. And remember that represents the fact, 0, 0 represents the fact that we have a 0 width, therefore we have no area. And 40, 0 is saying that when we have a width of 40, we would have no length, and therefore we would have no area. We can see our maximum here at 2,800. So when our width is 20, our area is 800. This is also known as our vertex of our quadratic function. Notice that the x value of this point, so the vertex is an ordered pair, it's a point. It's in this case, it's a maximum because our parabola is going up from the left, is going up to the maximum and then coming down. But we can see that the x value of our maximum or our vertex is the average of the x values of our two y-intercepts. So the x value for this point is 0, the x value for this point is 40, and the average of those two, or the midpoint of those two, would be at 20. And so our x value of our vertex is halfway between our two x-intercepts.